We present dynamic layer detection of a thin silk cloth using DenseTact Optical Tactile sensors. Interacting with cloth is required for many everyday tasks. Accordingly, robotic cloth manipulation has potential applications in various domains. For example, assistive home robots, elderly care, and manufacturing. However, cloth manipulation is challenging for robots due to cloth having complex dynamics, high degrees of freedom, and self-occlusions. A result of these challenges is that cloth often becomes folded or bunched up during manipulation. Thus, it's important that robots are able to identify how many layers of cloth are grasped for effective cloth handling. To address this problem, we developed a custom gripper equipped with DenseTact Optical Tactile sensors. To detect the number of grasped cloth layers, the gripper executes a dynamic rubbing motion and uses collected tactile information in a transformer-based network. This video shows one trial of data collection using our custom gripper. The gripper features a compact design using 4 Dynamixel motors and DenseTact 2.0 optical tactile sensors as fingertips. After grasping the cloth, the gripper performs the pre-programmed rubbing motion shown. The DenseTact RGB camera feed and 6-axis wrench estimation are recorded for the duration of the motion, along with the joint states of the gripper. The RGB videos are used to calculate optical flow, and the collected sequences of optical flow, 6-axis wrench, and joint state data are used to identify whether 0, 1, 2, or 3 layers of cloth were grasped. 92 trials were collected for each of these 4 classes, for a total of 368 trials of data. Here is the architecture of our classifier model. As mentioned, the model takes the optical flow, 6-axis wrench, and joint state data sequences as inputs. Each input goes through a feature extractor to capture notable patterns that differentiate between classes. The optical flow feature extractor uses a CNN structure, while the wrench and joint state feature extractors are multi-layer perceptrons. All extracted features are then concatenated and fed into a transformer encoder, which uses attention mechanisms to understand feature time dependence in the data. The resulting integrated features from the transformer are passed through fully connected layers and a softmax function to obtain a probability distribution across the 4 classes. The class with the highest probability is taken as the predicted number of layers. Our method achieved a test accuracy of 98%, with classification results shown in this confusion matrix. Out of the 56 test trials, only 1 was misclassified. These results show the effectiveness of using a dynamic rubbing motion, tactile sensor information, and a transformer-based model for cloth layer classification.